Hey folks, well, now that we've gone through the basics of optimization, and we've looked at kind of the four different levels that we might want to consider optimization at, right? The local block level, extended blocks or regions, getting into the subroutine level, and then the whole program. We want to get a little deeper into the analysis of the code that's necessary to perform better optimizations. So we're always working from this idea that we've got sort of a control flow graph that's showing us how data is moving through the different blocks of code, right? Where we've got these nodes representing our blocks and edges indicating that we've got flow going from one block to another. So what we want to look at is data flow analysis, where we work from this control flow graph and try and identify places where optimizations really can present themselves. And once we've got that, what we'll look at is using our single static assignment idea from way back when as the sort of intermediate representation of the code after we've got our analysis done. So again, that tends to give us a reasonably compact representation that's still got all of the information that we need to generate our desired code. So data flow analysis, well, control flow graph, data flow analysis, single static assignment, and then we'll see where we can go from there. Now, in the last couple of sessions, we looked at things like the value numbering system, where we used local value numbering for blocks, or super local value numbering for extended blocks, where we could look at kind of tree-like portions of our control flow graph and say, well, I can take a path along this and optimize it using our local value numbering. So I can perform some of the basic optimizations on that, taking the blocks along that path, and for the moment treating them as if they were a single block and optimizing them as if they were a single block. And as long as we're picking paths where we don't have to worry about sort of reconvergence and cycles and that kind of thing, then we can actually come up with a fairly good optimization from this, right? At least improve our opportunities for optimization. But again, that doesn't account for reconvergent paths, and it doesn't account for cycles, and we need some kind of deeper analysis for those, which is where we get into data flow analysis, and we'll spend a while on this. So let's see what we can get into here. Now, we'll look at this at kind of the subroutine level and then at the whole program level. So at those levels, you've got more complete information about a unit of the program, if you like. You've got all of the local variables and the parameter definitions for your subroutine. You've got the complete block of code up to the return point. So you've got reasonably complete information. Now, it does mean that you've got more complex analysis that has to take place because you've got a lot more going on than in a simple block. So that's where we have to kind of look at the edges between things. And this gets, more complicated by the places where within our subroutine we start making references to things that come from outside the routine, things that come from other compilation units, things that come through pointers or variable array indices, things that come through pass by reference parameters. So there are all sorts of things where we're making reference to things that exist outside the scope of the subroutine, and that tends to muddle our ability to do an effective data flow analysis. But we'll address these things as best we can. So where we're going to start with is what's called iterative data flow analysis, and we've already actually seen an example of this with our Liveout computations. So in Liveout, we had this static information we could calculate about a block, the upward exposed variables and the var kills and that sort of thing. So we had static information we could compute about a basic block, and we knew that information wasn't going to change. And then we could take this big collection of blocks and keep computing Liveout for each of them based on what's known about everybody else's Liveouts so far and what we know about our own block. And so we just keep doing that over and over and over again until nothing changes anymore, and we finally got a complete picture. So this is the kind of iterative analysis idea where we just keep iterating through the analysis on everybody over and over and over again until things stop changing. And usually the notion is we've got some things that we can calculate locally that are static, and then you just keep looking at what new information you have about the blocks around you and going over and over and over again until you've got the complete picture. So later on we'll take a look at applying similar techniques at the whole program level, but for now we'll look at it at just the subroutine level. Now, one of the things that's going to crop up in this a fair bit is the notion of dominating nodes and dominating sets. So the idea is, if we're thinking about a node n, then a dominating node for n is something that lies on every path into n, so something that you can't avoid on your way to n. So this is, at the subroutine level, we're thinking about from the entry block for the subroutine to the node n that we're interested in, what nodes lie on every single path in between. And those are the nodes that form the dominating set for n. So with our example here, let's say n0 is our entry point to the subroutine, and we're interested in figuring out what the dominating set is for n4. Again, it's just those nodes that lie on every path to n4. Well, there's only two paths here. There's the one that goes through n1, and there's the one that goes through n2. Obviously, n0 is on every one of these paths, n3 is on both of these paths, n4 is on both of these paths, n1 and n2 are not, right? They're each only on one of the two possible paths. So, dominating set for n4 is n0, n3, and n4. Right? Relatively simple concept, we just have to come up with a way to figure it out, and you can see the idea, how this would be useful in a lot of our data flow analysis techniques, in that this is identifying the things that we have to deal with for node 4, right? These are the things that are guaranteed to happen before node 4. All right, our algorithm for going through and computing our dominating sets. And this is going to be another one of those iterative ideas where we can compute some things about the node itself, and then we just keep computing things about everybody else until we know the final result. So let's say we've numbered our block, we've got k blocks, we've numbered them 0 through k minus 1, and initially we'll just say that the dominating set for each node is just that node itself, right? We know that that node is on its path because it's its path. So, and if we've got, eventually we'll make the realization that we've got n0 in all of them as well, but that's another story. So we'll start off with just this set of n individual dominating sets, one for each of the different nodes in our graph, and we'll keep going until nothing changes. So we're going to have this while loop that basically recomputes the dominating set for everybody and sees if any of them changed. So we'll start changed off at true, so we get into our loop the first time around. And inside the loop, we'll say, okay, for this pass, let's say changed is false until we actually change something. And then we'll go through each of the nodes. Here I've skipped n0 since there's nothing before n0, so we're not going to wind up adding anything to it. So for each of the nodes from 1 to k minus 1, what we'll do is compute a temporary new dominating set for it and see if that matches the one that we've previously calculated. So the way we'll figure it out is to say that it's the node itself, and then anything that's in the dominating sets for all of its predecessors. So, if something lies on, so thinking about n4 again, if something is part of the dominating set for n3, it's going to be part of the dominating set for n4, right? n3 is the only thing before n4, so if it goes through all of the paths to n3, it's got to go through all of the paths to n4, or it's got to be on all the paths to n4. And similarly for n3, if there's something that's in the dominating set for n1 and in the dominating set for n2, then we know it appears in all of the paths into n3. So that's the idea that we've got here, is we'll go through and see what things are in the dominating set for each of our predecessors, take the intersection of that, and that gives us the revised dominating set for our current node. So basically we're going through and saying, okay, well, if I've got updated information on my predecessors, then I can come up with the updated information for me. And that's the notion here. And we just keep recomputing this and recomputing this until nothing changes anymore. So if we were going to look at that same example again, on the first pass, we've just got Each node has its own, just itself as its dominating set. And then on the second pass, we'll just use the values from the preceding pass for the moment. And say, okay, well, so on the second pass, n0 is obviously not going to change. n1, what's in the dominating set for everything before us? Oh, wait, there's only one thing before us, and it's n0. What's in n0's dominating set? n0. So that's on every one of them, so we can add n0 to ours. Same thing in n2. Right? n0 is in the dominating set for the node before us. There's only that node before us, so we can add it to our dominating set. Now n3, again, assuming for the moment that we're working off of the old values for the dominating sets, for n3, all we know is that the dominating set for n1 was n1, the dominating set for n2 was n2. There's nothing that's common between those, so there's nothing we can add to n3, so we just stay with ourselves. For n4, we've only got one node before us, so anything that's in its dominating set is going to be in ours. It's got n3, so we can add n3 to ours. Now, if we've got a reasonable, what we could actually do as we're going through this is use if we compute n0's first and compute n0's second, then we can use those when recomputing n3, and we can use the updated value in n3 for computing n4. So we can actually cut this down a little bit if we're working from the most recently computed value for each of our nodes. However, so if we continue on, we make another pass. Nothing's changing for n1 and n2, right? We've already got exhaustive information for n0, so nothing's going to change for them. For n3, we can look at the previous values for them, and now we see n0 in that last pass crept into both n1 set and n2 set. So now n0 can go into ours. If n4 is looking at the old values for n3, nothing changed there, so nothing changes for us. And then on that last pass, again, nothing changes for n0, n1, n2, n3, since nothing changed for n1 or n2 last time. But n4 this time sees that, oh, n0 crept into n3 set. Now we can add n0 to ours. And if we do this one more time, we'll see that nothing changes, and so we've reached that sort of stable point. So this would wind up being our collection of dominating sets for the different nodes. Now, this is guaranteed to terminate, right? There's only so many times you can go through this before you've covered every possible update on the preceding path, right? If you look at the length of the path that's feeding into you, there's only so many times you can iterate through this before you're going to reach a stable point. And there's only k nodes in this, so these things can only get k bigger, so there can be only so many passes you can make through your through this algorithm. What we can do is, again, to improve the efficiency of the calculation process by looking at these nodes in a suitable order, right? If we make sure that before we recalculate n3s, we recalculate its predecessors, and before we recalculate n2s, we recalculate its predecessors, etc., etc. So if we can come up with an ideal ordering instead of this just kind of blind, oh, well, I numbered them 0 to k, so I'm just going to do 0 to k. Let's come up with a better ordering for what sequence we go through them in on each pass. And this is where our reverse post-order traversal comes in. So we're used to the notion of a post-order traversal, where we say, when I'm going through and processing a tree, the first thing I'll do is process the children of a node, and then I'll process the node itself. So we make a recursive call on the children first, and then come back and process the current element. So that's a regular post-order traversal. If we get our post-order traversal to number the nodes in the order that it processes them, so the first node that it actually completes gets value 0, the second node it completes gets value 1, the third node gets value 2, etc., etc., etc. That would be the ordering for our post-order traversal. What we're going to do for the reverse post-order traversal is just reverse that. Just take the exact opposite order. So we sort of calculate the post-order traversal and take the opposite, if you like. So the algorithm is reasonably straightforward. So order n will be the kind of which position we'll finally want to visit it in our dominating set calculations. Again, we're assuming k nodes, and what I'm going to make use of in our little procedure here is I'm going to assume that we've got this global variable visit num that's going to be the post-order traversal order number for the node. So we started at 0, and for each node we'll initially assign an order of -1 just as some default value so we can see if we've actually given a value to it yet or not. So our reverse post-order traversal takes a node and goes through and does our, oops, that should be an RPO. So for each child of n, we'll do our RPO on the child if it hasn't been visited yet. So we'll check. If it's already been visited, it's already got a number, we don't need to process it. So we'll look at the child, see if it's been processed yet. If not, then we'll call RPO on the child. So we're going off and doing the children first, and then eventually coming back and doing the current node. So for the current node, we'll assign it the current visit num, or at least the post-order traversal would assign it visit num. We want to assign it the opposite. So if it was going to get position 0, let's say we had 9 nodes. If it was going to get position 0, we want it to get position 8. If it was going to get position 1, we want it to get 7. If it was going to get 2, we want it to get 6, etc. So we're just essentially calculating the reverse of it here. So taking the post-order traversal number, taking the opposite, and then bumping up the order number for the post-order traversal. So we're just going through this over and over and over again until we've completed the processing of the whole tree. So if we go back to our same old algorithm, if we go to do this, if we're looking at n0, it's going to say, oh, I've got to do the children first. So let's say it does n1 first. Looks at n1, oh, I've got to do the children first. Looks at n3, oh, I've got to do the children first. Looks at n4, no children, so I can assign this, visit num is 0, so I'll assign this 4 minus 0, so this actually gets value 4. Then we back up. N3, we've got no children left. Visit number is now 1, so it's going to get position number 3. We back up. This has got no children left, so visit number is 2, so we can give it a value of 2. We come back here and say, oh, I've still got another child to process. It goes off to N2, which goes to do its children. Says, oh, nope, that one's already been processed. So this one would get visit number 3, so order number 1. And then finally we come back to this one, and it would get visit number 4, so our order number 0. So the post-order traversal would have gone through and done 4, 3, 1, 2, 0. So we're doing the exact opposite. Right? We're saying that our reverse post-order traversal sequence is going to be n0, n2, n1, n3, n4. And from the point of view of dominating sets, you can see that this makes sense. We're making sure that we get n0s updated before we try and update n1 and n2. And we're getting those updated before we try and update n3. And we're getting that updated before we try and do n4. And so when we're calculating the dominating set for n3, for instance, we've already done an update on n1 and n2. So we're getting more complete information before we try and do this. And when we're doing n4, we've got more complete information for n3, so we're using that in our n4. So hopefully we can cut down the total number of iterations through our algorithm, right? Which is exactly what we're kind of hoping for. All right. Now, again, the dominating set algorithm has some similarities, or a similar feel to it, if you like, to our Liveout calculations. Right? For the dominating set, we were looking for nodes that appear on every path into a node. For Liveout, we were looking for things that appear on any path out of the node. So we can actually make use of this kind of reverse post-order traversal for Liveout as well to improve the efficiency of our Liveout calculations. But we do have to make some tweaks to the graph that we're basing it on first. So if we go through and take the edges in the graph for our Liveout computations, if we just reverse the order of those, then we can start making use of the reverse post-order traversal and try and get a more efficient computation there. Now, it's not perfect. This does tend to come up with, if you like, overly pessimistic assessments of our opportunities for optimization. Essentially what's happening is that because these things aren't looking at the logic as to when a particular path is used, you've got no information about the relationship between one edge on a path and some subsequent edge on a path. We assume that it's possible to take every single path in a graph. So if we've got the graph shown here, then we assume that it's possible to do A, B, C, it's possible to do A, B, and then this other one, it's possible to do this other one, and then, I'll go on to N3 and do C. We assume that any path is possible. Logically, that might not be the case because of what's going on in the program. Suppose in N0 we've got something that says if X is false, then take path A. And if we've got something in N3 that says if X is true, take path C. Then that means that there is no possible way that, assuming X isn't changing, there's no possible way for us to take both A and C. So this A, B, C path would be impossible. But there's no way for our iterative analysis technique to know that because all it's interested in is the existence of the paths. It's not looking at the logic as to whether or not they could possibly genuinely happen during execution. So it is giving you overly pessimistic assessments. Some other issues come up in terms of ambiguity. If we've got, again, because we have to take the if you like, most conservative approach possible, right? We can't gamble on something being okay. If somebody's using, let's say, a variable as an index into an array and setting a value in the array, then our algorithms have to treat it as though that could be any element of the array. So if you set one value in the array, the algorithm has to kind of treat it as if each element in the array got reset, because we don't know which one did. Similarly, if an algorithm uses a pointer to set a value, then we have to assume that anything that pointer could have pointed at got reset, because we don't know which one did. It gets even worse if you've got pointer arithmetic allowed, because then it's not just things that the pointer could point at, it's things that the pointer could get to through an offset. So these things really kind of constrict what the compiler can do, and quite often if you're making use of pointers, the compiler will actually avoid putting values into registers if they're things that the pointer could refer to, right? If they're a possible target of the pointer. So it does really limit the effectiveness of some of these iterative algorithms. Now, there are, we've looked at sort of the dominating set and the Liveout set, and we'll come back and make use of these later. But there are a few other very similar algorithms where we're computing different metrics. We're doing analysis on different metrics that use a very similar algorithm and have a very similar look and feel, as you'll see. So one of them is looking at expressions, right? We've got all of these expressions, x is assigned a plus b, where we want to know where that expression result might get reused. So where that a plus b result might get reused, because that gives us a good opportunity to avoid recomputing it and just making use of the value that we had earlier, right? Which is one of the big things that we've talked about, is reusing earlier computed values. So what we would like to be able to do is, when we compute an expression, see where it flows through to, and where we are performing computations, being able to see which expression results are available to us. So what we'll look at first here is the available in. So let's say I'm at some point P in my graph, and I want to know which expression results are available to me here. Which things can I reuse at point P? So we'll say expression E is available here if on every path from the entry point to the subroutine to where we are now, E has actually been evaluated, and none of the sub-expressions it uses have changed since then, right? Because that means that whatever it computed at its point of evaluation is still valid. So the set available in for a node n are the set of expressions that are available in n. We'll have a couple of related metrics. The downwardly exposed expressions of n are the things that are evaluated in n and not subsequently changed. You know, where we compute some expression and don't change the sub-expressions it used afterwards. So whatever it was we computed is still valid at the end of n. Conversely, the expression kill set of n are the set of expressions where we change one of their sub-expression values. So the things where we messed up a value that was used by a previous expression, so that previous expression is no longer available. So those last two, just like the upwardly exposed expressions and the var kills that we used for Liveout, these are things that we can compute locally within a block. Just look within the block and see, you know, what things do we compute and then not change their sub-expressions, right? That's easily done in a pass through the block. And similarly, expression kill, what sub-expressions do we set? What things do we change the value of? Again, easily computed in one pass through our block. And then for the available in, if we just go through and compute these things locally for each block, then we can go through and recompute what's available for, or what's downwardly exposed and not killed from each of our predecessors, and just keep recomputing that over and over and over again, right? See what flows through to us, what the available insets become over the course of time. And again, we get this nice iterative algorithm to go through and find out eventually what sets of expressions are available at the current node n, right, at our current point p. So, very similar algorithm. Again, obviously useful in terms of identifying which things we can make use of without needing to recompute. The idea of what's downwardly exposed ultimately might also allow us to go through and identify which expressions are dead, if you like. A similar idea will be the set of variable values that reach a point in our control flow diagram. So if I've assigned a value to a variable, does that assignment of that value to that variable reach me, right? Reach my current point. So reaches will be the set of definitions that reach n. So a definition is just an assignment of a value to a variable. The downwardly exposed definitions are things that we have assigned a value to, right? Definitions we've made that aren't subsequently changed. And the def kill are the definitions that we change, right? So again, you can see a very similar algorithm creeping out for the computation of this. Now, ultimately, we'll want to expand this to whole program analysis, but again, there are a lot of complications that we have to deal with at the whole program level. And we've got to make worst-case assumptions about what each subroutine does. So we have to think about, what is it possible that a subroutine can actually alter? What are the kind of side effects that a subroutine might have? And we have to assume that those side effects actually happen, right? Because we can't trust that they won't change a value. So anything that is passed by reference to a subroutine, we have to assume is changed. Anything that is referenced by a pointer that the subroutine has access to, we have to assume the subroutine has changed. Any global variables that the subroutine could possibly use, we have to assume it changes. So we'll start coming up with ideas like may modify, right? The set of things that a subroutine of function f might change. And we'll represent this as just the set of names of values that might get changed by f. And again, we can compute locally in f. We can take a look at it and see which things it does actually change. And then look at, well, so here's the set of things that I know I change, or that I can possibly change. But the problem is I'm also going to make calls to other functions. So when you call f, then things might get changed by the functions that f calls. So we have to look at each of the successors. For everything that f calls, we have to look at the may modify set for it. And for each thing that it calls, we'll have to look at the may modify set for it. And so you can see another one of these iterative algorithms evolving where we go through and say, okay, well, compute it locally for everybody, and then just start recomputing based on, oh, I see that G also changed this. And so we modify, or we update F's set. And then in the next pass we find out, oh, something G called modified this. So now we add it to F set. And then you do another pass and say, oh, something that G called something else that modified things. So we have to add that to F set. And you just keep going through this process again until nothing changes. So these iterative algorithms will keep coming back in our data flow analysis. All right, that might be a good point to leave it for the moment and come back with more later.